So welcome everyone, my name is Martin Cereza and I'm going to talk about effectful improvement theory. In this presentation I'm going to talk about programs optimization. Proving that the program's transformation is actually an optimization is hard since we have to check two different aspects of computation, what and how the program is computed. In particular, we want to improve how the program computes without changing what it computes. So we want to prove an intentional property without changing the meaning of the program. But how can we check that? How can we be sure that we are improving a program? Or even worse, what does improving a program mean? These questions were answered in the 90s by David Sand's work, where he developed a relational analysis framework called improvement theory based on the idea of improvement. He based his theory on the definition of observational approximation given by Morris in 1968. He defined that the term M is approximated by the term N if and only if any context that observes M termination also observes N termination. Here we are referring to context as just programs with holds. So basically we are observing how they behave based on the relation between terms and values. For example, the beta reduction rule defines two observably equivalent terms. A beta reduction term is approximated by the resulting term of the evaluation rule, and also the other way around. So Sands defined a similar notion of observable approximation, where he added an additional observation, the cost required to compute a term. He redefined the evaluation relation to keep record of how many steps were performed on the evaluation of a term, and defined the notion of improvement, where a term M is improved by another term N if and only if, in any context, the cost required to evaluate N is not worse than the cost required to evaluate M. Note that we have two observations here. One is the same as observational approximation that we did before, and the other one is that the cost is not worsened by the evaluation of the terms. For example, we can see that the result of the beta reduction of the application of the beta reduction rule is an improvement, since in the result of the rule we require one step less to evaluate it. So improvement is actually a bit more expressive than observational approximation, since it can distinguish between these terms, right? But as we said before, we know that the difference between these both terms differs only in the amount of step made by the evaluation. In this case, in particular, it's just one. It's the step made by the evaluation, by the beta reduction rule. So we can define an unary operation called tick that adds 1 to the whole program cost and express exactly the difference between these two terms, right? They are semantically equivalent, but one is better than the other exactly in one tick. So what about effects? Suppose we have a family of probabilistic operators O plus P that behaves as its first argument with probability P and as its second argument with probability 1 minus P. So how do we compare two probabilistic programs? Can we use the same definition as before? Or do we have to change something in the evaluation, or we have to change something on the observations that we were making, etc. So we can see an example here. Suppose we have a family of uniform sampling functions indexed by the natural numbers, such that uniform sampling n samples a natural number between 0 and n uniformly. So given a closed probabilistic program M, can we prove that sampling a number and not using it in M is improved by just the evaluation of the program M? Can we safely remove the sampling operation? Well, we are going to answer this question in a bit. So following some steps, we present the definition of effectful improvements as a refined notion of effectful observational approximation. Recently, Dal Lago et al. Updated the definition of observational approximation for effectful calculus. The idea is similar to the previous definition, but now more complex observations can be done. Effects are introduced by new operations in the calculus that are later interpreted by a monad T, generating a monadic evaluation from terms to effectful values. But now we need a mechanism to compare effectful values, and that is exactly the role of the monad relator gamma. A relator is a lifting mechanism that takes a relation between ground values to a relation between effectful values. So we have that the effects produced by the evaluation of an effectful program are interpreted by monad T and then compared through a relator, in this case gamma. Since we are working within a relational calculus, relational theory, we are going to work inside the set category. So everything are sets, and every functor is actually an end of functor within sets. That's it. So the relation employed in this case, in this definition, the relation U simply relates every value with every other value. Lifting U with the relator gamma simply compares only the observations made by the relator without checking the values computed. Same as before, where the only observation was divergence, but we didn't actually check anything about values that were computed. As a result, we have that the term M is approximated by a term N if and only if in any context the evaluation of N generates the same observable effects as the evaluation of M. For example, assume we have a set EX of exception symbols, and for each symbol define an operation that raises an exception. So we have the classic lambda calculus plus a set of operations representing exception. We use the classic exception monad with a special case denoting divergence. So we have three possible cases. Either the evaluation of a term diverges, raises an exception, or returns a value. We can interpret raise E as raising that raises the exception E as injecting in the left and then in the right the value E, the element E. So and we can also define the eta or the return function, as just injecting a value with in the left and then in the left. And the bind operator simply performs case analysis over the first computation and then propagates its behavior. So now we need to define a relator gamma for the monad E that lifts relations between sets to relation between effectful sets, in this case with exceptions. So gamma takes a relation R between X and Y and returns a relation gamma R between E of X and E of Y, where elements are compared by case analysis on the first element. So either we have that M is bottom or is an exception, and then N is also the same as exception, or M represents a value and also N represents a value U, where such that V is R related to U. So putting all together and unfolding the definition of observable approximation, we have that M is approximated by N if and only if in any context either M diverges, raises an exception, and then so does N, or terminates and then so does N. And we can do the same for this kind of effect. For example, non-determinism. We can add a binary operation O plus representing non-deterministic choice. We can use the power set monad to interpret this effect, where the result of the evaluation of a term is the set of all possible values that the evaluation of M can take. And we can interpret the binary O plus operator directly as the binary union of sets. And we can use a relator that is simply the intuitive extension of a relation from elements to sets of elements. And unfolding the definition of observational approximation, we have that M is approximated by N if and only if in any context that M terminates, it also does N. Note that in this case, divergence is represented as the empty set, meaning that the evaluation of a term does not reach any value. So what about cost? Well, following the same idea proposed by Sand, we just add cost as an observable effect. And in order to do that, we need a cost-aware evaluation to compute the cost needed to evaluate a term, a cost-aware monad to keep records of the cost required, and a cost-aware relator gamma capable of comparing effectful values with their costs. So remember that at the beginning of this presentation, I introduced the classic definition of improvement as a refined notion of approximation, and we explored its expressive power through the addition of a new operator called tick. In this case, we are going to introduce the tick operator first and then derive all the required machinery from it. For example, we revisit the exception system, where we simply equip each value with a natural number representing the cost required to compute it by composing the monad E with the product with the natural numbers. This is an arbitrary choice, and we are going to explore a different one in a bit. But for now, it's enough with this composition. We also modified the relator, composing it with the product relation with inverse natural order, so we can interpret the tick operation just by lifting the function that adds one to the cost accumulated in the second component of the pair. As a result, we have a definition of improvement derived from the definition of observational approximation, where M is improved by N if and only if either the evaluation of the term M diverges, throws an exception E and then also does N, or reaches a value with cost M, and then N also reaches a value with cost N which is less or equal than M. So in this case, we reuse the same machinery we had for exceptions to take cost into account and derive a notion of improvement for this effectful calculus. And we can do the same for non-determinism. We get a cost-aware monad where each value is equipped with a cost just by composing the monad with the product with the natural numbers, and we get a cost-aware relator adding the observation that the cost do not increases by composing gamma with the product with the inverse order of the natural numbers. And we can also interpret the tick operation as the lift of the successor function on the second element of the pair. So finally, we obtain a definition of improvement that says that M is improved by N if and only if in every context, every possible value in the valuation of M, for every possible value in the valuation of M, there is a value in the valuation of N that require less or equal cost to be computed. So from the previous two examples, we can extract what we call the cost system. Define C of X as the product of X with the natural numbers. Pure or return is just a function that is just the function that bears a value with 0. And we can define the function add that adds a natural number to the second component of the pair. And finally, the divine operator simply accumulates the cost given by its first argument. We can also define the cost relator, where defined as the product of the relation R with inverse order of the natural numbers. So, summing up, we started from the definition of observational approximation, where we needed a set of operations sigma, a monad T that interprets the effects generated from the operations, and a monad relator gamma for T that compares effectful values. And Dal Lago showed us how to get an observable approximation definition for that effectful calculus. From there, we can add the tick operator. We can define a new cost-aware monad simply by adding the ability to accumulate cost in a similar way to the cost monad, by just interleaving the effects of counting ticks or accumulating ticks and interpreting the effects generated by the operations. And we can compose the relator gamma with the cost relator C to be able to compare cost as well to compare effectful values. And since relators are closed under composition, we get a new relator that compares both effects, the accumulated cost and the effects produced by produced by the operations and interpreted by the monad. So we can finally obtain a notion of effectful improvement. In the Haskell community, this monad transformation is known as the greater monad transformer of T with the additive monoid of natural numbers. So, moreover, we can apply this recipe for the probabilistic operators presented at the beginning of this presentation, where here we have a family of operations, O plus P, same as before. We use the monad. You use the sub-probability distribution monad to interpret the effects, where the valuation of a term is represented as a sub-distribution, indicating for each value the probability of being the result of the valuation of the term. And the subdistribution relator simply checks that the sum of the probabilities of related sets of values actually increases. And as a result, we can compare probabilistic programs, and moreover, we can prove improvements. So, given a closed term M, our task is to show that we can safely remove the unnecessary sampling operation presented at the beginning of this talk. Following the evaluation of terms, first we consume the let constructor, producing a tick, and sequencing the evaluation of the uniform sampling, and with the result of that evaluation, we continue with the evaluation of M, replacing every free occurrence of X with the value sampled. Since M is a closed term, there is actually no free occurrences of X, so M remains the same after the substitution. And also, since the uniform sampling term or program generates a uniform sampling, a uniform probability distribution, we can safely remove it without without modifying the distribution generated by the valuation of M. And we have just proved our first improvement in probabilistic calculus. So, effectful observational approximation and improvement depend directly on what we are observing, and that translates directly to the notion, to the definition of the monad relator employed in the definition. So, since there are monads that accept different kinds of relator, we will have different notions of improvement, one for each relator, as is the case of non-determinism, which accepts 3 different relators, and each relator defines a different or a possible different notion of improvement. Here we present the three relators for the non-determinism monad, for the power set monad. Each relator is named after their power set domains versions in the field of domain theory. The intuitive idea is that Howe's relator, which is the one we employed in this presentation, is optimistic and checks that for every possible value in the evaluation of M, there is a better or equivalent value in the evaluation of N. Smith is pessimistic and checks that for every possible value in the evaluation of M, there is a worse or equivalent value in the evaluation of M, and Plotkin's checks both. Okay, so as we have seen, we can apply the recipe described before and derive a notion of improvement for different kinds of effects. But there is a problem. So far we have equipped each value with the cost required to compute it, but there are some cases where we might have other elements that we might have cost and we might want to compare them. For example, within the exception calculus, we might want to compare the cost generated by the cost required to compute a program that ends in an exception. For example, what is better, to waste the unit of cost and raise an exception, or to raise an exception without wasting computational resources? So far, in the definition of exception improvement that I showed you before, exceptions do not have any associated cost, so we can't compare them, and as a result, both computations are actually equivalent. But there is a solution to this problem, which consists in providing a new tailor-made monad with its relator that equips exceptions with cost too. Here we present an example which I call G cost, which represents the idea of having a global cost notion. So we can observe the cost required to compute exceptions, and we can distinguish the two terms described before, where it is actually an improvement to avoid wasting a unit of cost, and we can actually prove that raise an exception cannot be improved by wasting some computational resources and then raises the same exception. But there is a problem with this solution, since it is a tailor-made monad. We actually have to prove that everything works out, and which is what we have if we derive the notion, if we use the derived notion from the recipe that I showed you a few slides before. So, conclusions. We presented a simple way to derive the notion of effectful improvement for effectful observational approximation, from effectful observational approximation, by adding the operator of a new operator called tick, and perform a simple transformation on the monad interpreting the effects. We noticed that different observations lead to different notions of improvements, and we also noticed that following the recipe might not return a very expressive notion of improvement, and we also see that there are other solutions. We also proved an optimization in a probabilistic calculus. As future work, we are working on a toolset of general algebraic properties of improvement to simplify future proof in other calculus. Try to get a general or a general abstract toolset to simplify future proof. In the area of cryptography, cryptography proofs are based on a sequence of gains where in each step of the proof we have to prove that the adversary does not observe any change in the game. The idea is to introduce the notion of improvement to also perform intentional analysis in such proofs. For example, we can count the number of times an oracle was called, for example, to prevent second channel attacks, etc. And we are also trying to prove some classic known optimizations, but with the presence of effects. For example, the common source expression elimination, which is a classic compiler optimization. We actually prove that it is an optimization, it is an improvement where the only observable effect is divergence, which is the same as Sands did in the 90s. But we are trying to explore new ways to prove it, for example, in the case of exceptions. Or try to decide what kind of effects, or relators or monads, or how they behave in order to observe the, different kind of optimizations. And anyway, I am actually looking for new applications of this theory. So if you want to apply this notion of improvements to another theory or field, just contact me. This is my email. Just contact me to everything. I open to new kinds of work. So thank you very much, and I'll see you in the Q&A section.